I will be talking about localization and clustering algorithms for wireless sensor networks. I'll present, I am from Kettering University in Flint, Michigan. And this is an area that I've been working on for some time now, presenting algorithms, in various forums. I'll start with simply introducing wireless sensor network and the technology associated with it. And then I'll introduce the problem of localization. Both are different problems of wireless sensor networks, but I'm approaching it a little bit from the structural point of view. So I've combined the two together. And then I'll present, there are multiple algorithms available. I'll present the one that, I've recently published and the results associated with that algorithm. And then I'll also introduce the problem of clustering, and I'll present an algorithm and a result for clustering. So two problems related to wireless sensor networks. So what are wireless sensor networks? They are networks consisting of small sensors which are distributed in the field of choice, and they collect information and about the physical phenomena, and then they sort of collect the information and give it to a node in there, and finally send it off to a base station if required for further processing. So we'll see some examples in just a minute. So there are several challenges with deploying wireless sensor networks. One of the challenges being we have very limited battery lifetime for the sensors. And when you run algorithms, they run on slow embedded processor that's within the sensor, and then with a limited amount of storage. So what we would like to see is that these sensors stay alive for a long time. They receive and signal information as needed, and they don't just get off the battery life. Examples of where wireless sensor networks may be deployed is that, first of all, we may think of, it's of course in your smartphones and your smart homes, where you can sense the temperature of the room and turn on the air conditioner, etc. Or you can be in a landmine, detecting landmines, in a military location, or you can detect chemical weapons. You can deploy sensors in those locations, or you can find, code blue in hospitals, watching patients in different rooms and alerting when there is a code blue situation. And of course, traffic monitoring has a lot of sensors associated with it. So there are many, many applications where these sensors get deployed, and and we want to be able to do certain work with them, self-organize them. We may not have manually be able to go and relocate them because they are deployed in locations that you may not reach after they are deployed. So let's talk about what is localization. So what happens is that when you deploy these sensors in whichever location it is, they tend to move. If you're in a war zone, if you deployed it in some sort of equipment, the equipment moves, so the sensors have moved. You don't know their real location after a certain period of time after deployment. So the question is, how can we find their real location, which is called localization, so that you can go on a rescue mission of that vehicle, of the person, or of the location that you are. So the idea is to try to find the geolocation of sensors after the initial deployment, after a certain period of time, without having to go and intervene, from that location. So one might say, well, why don't you just put GPS on these sensors, and then it'll be easy. Then you can actually locate exactly where they are. The problem is with GPS, you tend to use a lot of battery, and then very soon the sensors will die and they'll not be able to sense and transmit information anymore. So we would want to reduce using GPS into sensors. We may use it on a few sensors, but we may not be able to use it on every sensor that we have deployed. So localization can be done in a 2D or a 3D environment. So what we are looking for is algorithms that can tell us exactly where these sensors are located after we've deployed them. And we want to do that in multiple approaches. And what is the data that is available for us to localize or to find that location information? The answer is that, of course, you have some nodes called anchors whose location we know, and we are trying to find all the other nodes in relation to that anchor. And using distance information and the geometry, we may be able to find the exact location of each sensor. And that's the goal. So we have some limited anchors with location information available, either because they have not moved, we make sure they don't move, or we make sure they have a GPS. Either way, we know the location of the anchors. The rest of the nodes, we do not know the location. So the other thing is we assume is that there's possible distance information between some of the nodes, and that we'll see how that distance information can be obtained. We may have angle between sensors available to us. So we may be able to look at the angle. It's a very rich area of research, and there's been lots and lots of publications and research going on with finding localization, auto localization or self-localization. And here are many approaches that have been tried. One can use a distributed or a centralized algorithm. One can assume there are no anchors at all, or one can assume there are anchors. One may assume distance is available. Distance is also called range. Or we may assume no distance information is available. We may assume there is the sensors move while the algorithm is running, or they're stationary during the algorithm of the localization. Or we may send a robot to recover the sensors. It's called robotic assisted. And we may improve the algorithm sequentially, or we can do a one-shot global algorithm, etc. So there's multiple approaches that has been tried. The one that I try is, we'll talk about, I do anchor-based algorithm. There are a few anchors in my algorithm. That means they are the nodes who know their location ahead of time and they don't move, either because they have GPS or because they haven't moved. I also do range-based, which means I know the distance between sensors. So it looks like a graph. So essentially it ends up being a graph now. So range, how do we find the range? The strength of the signal arrival, they can tell how far a sensor is. So they can tell how far it is, but they don't know exactly where it is. Okay. So the approach that I take is based on graph localization. So if you think of wireless sensor networks in this situation, they look exactly like a graph with nodes and with links. So we don't know the location of the nodes, but we know the edge width or the edge weight, which we call the distance between the nodes. So the question becomes now a graph problem. So is this graph localizable? So I can take the wireless sensor networks, abstract it as a graph, and ask myself the question, is it possible that I can find the location of these nodes just given the distances between them? And the answer is being studied many years ago with graph theorists. And they say that, well, sometimes it's not even possible. For example, if you had 4 sensors located in the corners and somebody told us the distance, they may be located there, or they may be located like that in the lower picture. So we call it not rigid because there are multiple locations possible with the same distance map. You don't have to change the distance map. On the second picture again, which is generically rigid, what happens is that there is a flip ambiguity. Notice that when I flip the triangle, distances are still obeyed. The distances between nodes on the top diagram and the bottom diagram are exactly the same. However, the locations of the nodes are different. So when you cannot locate the sensors, then it becomes a problem for rescue missions. So we want to be able to locate the sensors exactly as to where they're located. So we are looking for the property called global rigidity, which means there is only one way, given those distances, there's only one single way, one single position where these nodes can be in. And that's called strictly rigid graphs or globally rigid graphs. And we look for these type of graphs or networks so we can localize them. So the 2 major questions we have to ask is the network localizable? Can we find if the graph is globally rigid computationally, given the network? And only if it's rigid, then I can find the location. So there are 2 related questions. So given a wireless sensor networks, is the underlying graph globally rigid, and how do I find it? If yes, then how do I find the location of them? So 2 questions to answer before we give the location of the nodes. So the answer is, the first one is good news. We can find if a graph is globally rigid, and there are some techniques for that. There are some graph theoretic algorithms that will help us. And one of the theorems that will help us is called Lamont's theorem, who came up with a theorem that said that it's generically rigid if it has no induced subgraph. Not very useful, although it's a good theorem, because we can't try every induced subgraph to see if it has this many edges. So it's not computationally feasible, but theoretically it's correct. But we cannot try every single subgraph, which will take exponential amount of time. So even though Lamont's theorem gives us the theorem to test for globally rigid, for generic rigidity, it doesn't give us an implementable algorithm because it's going to take exponential time. So we have another theorem, Pebble game by Jacobs, which actually gave us an algorithm to find generic rigidity. So having found generic rigidity, how do I move to global rigidity? Remember the 3 types of rigidity we talked about. Not rigid at all, generic rigid, globally rigid, and we're shooting for globally rigid. So there was another help that came and told us exactly when is a graph globally rigid. They said only if it's redundantly rigid and 3 connected, both of which are checkable using algorithms. So basically we are able to check, given a network of thousands of nodes, whether it is localizable or not. That doesn't mean we know the location. We can only say yes or no, whether it's localizable. So global rigidity can be checked in polynomial time. So we have the answer to that. So the 2 questions now come up are, what if the network is not globally rigid? It's not meant to be globally rigid. You're just throwing some sensors out there for sensing. It doesn't mean the underlying graph is going to be globally rigid. How do we deal with if it's not globally rigid? So we have to answer that too. And once it's globally rigid, then how do I do localization? That's another question that needs to be answered. So the first question that we approach, what if it's not globally rigid? I still want to localize at least the portions that are localizable. So what we did was we tried to find small rigid graphs and then grow the rigidity, find larger and larger rigid regions, which means we are trying to localize as much as we can. We may not be able to localize the entire network, but at least we find the locations of the majority of the sensors. And that was the first algorithm that we created. And the way we did that was we found the smallest possible graph that's globally rigid, which is called wheel graph. So you can identify wheels in the network, and these are globally rigid. And then we keep adding something to it to make it make larger and larger globally rigid graphs. So that way, at least we have large regions that are localizable, that are globally rigid. And this was a theorem that was created in one of my papers, which is called 2-region merge. If I know that 2 regions are globally rigid, this theorem tells me what should happen for the entire region and region 1 and region 2 together to be globally rigid. And there are 4 conditions. It says you should have at least 3 vertices in common, or 2 vertices and 1 edge, or 1 vertex and 2 edges. And then one more condition that says, or there should be 4 edges between them. So this theorem tells me how to grow a region. So I took 2 wheels, how should they be connected to make a new structure that's globally rigid. So I'm able to grow the global rigidity. And so that's basically the theorem version. And now I also then created a 3-region merge. So if I have 3 regions that are globally rigid, can I combine them? What should happen for the entire graph to be globally rigid with the 3 regions combined? And there is a condition involving 7 edges here, which we won't go into, but that's. So using that, what did we achieve? Here is our results where this is a graph. And then I found these are the regions that are localizable just by running the algorithm, saying that notice that some nodes are not localizable because they're not very strongly connected to the other nodes. Everything depends on the distance information that I have at each node. Some of the nodes have very tightly connected. As you can see, there are some K4s and stuff, complete graphs here. These are globally rigid regions that we found, and we grew them. We started with a small globally rigid and we kept growing them. So now at least we can tell majority of it is localizable. Some of it, I cannot find those sensors. The sensors that I can find, we're going to try to find them by finding the location. Now, when the network becomes dense, this is a sparse network. When the network becomes very dense, the whole thing becomes globally rigid. So which is what we expect. The more information you have relative to other nodes, the more likely that you can find its location. So the more connected it is, the more dense it is, obviously you're going to see that the whole thing is globally rigid. In fact, there are some theorems that says what is the connectivity that we need in order to, what is the radius of the network we need or the connectivity. So here, I'm going to try to show you that when the radius is very low, like 12, which is considered low sparse graph, sparse network, notice that number of nodes localized is very less. It's only 45%. I can only locate 45% of the nodes. But the more radius I have, which means I have a radius of 16 and higher, I'm able to localize more and more nodes. I'm able to find the location. So the more sensors are deployed at a certain location and they are located close to each other, there are more distance information, I'm able to locate them better. But they're far apart, they don't give us information about each other. And that's what the theory tells us, that therefore I'm not able to localize too many nodes. So the next question, of course, a big question that we say, okay, I found globally rigid subgraph, which means as much as I can localize, I'll try to localize it. But how do we actually localize it? Is there a way to find the location? That also turns out to be a very difficult problem, There's a theorem that says even if a graph is known to be localizable, actually finding the location is NP-complete, which makes it even more challenging because it's now an NP-complete problem. Knowing that it's localizable, finding the location is still NP-complete. So we need to do some sort of approximation algorithm here to find the location. And we have something called MDS map, which is multidimensional scaling algorithm, which if you give the distances, it'll compute the locations. And there's a theorem on how it does it, but it's not 100% accurate, but very good. It's extremely well accurate. So we may be able to find the sensors close enough that we walk around that area, we may be able to find in a few meters the actual sensor. So it's still a decent approximation. So much for localization algorithms. Now I want to move on to what we call clustering, which is a different problem, but it's still the same basis. We still have sensors, we still have wireless sensor network, and we want to look at some clustering problem and a clustering set of algorithms. What is clustering in the first place? The idea is that, remember, the sensors actually sense data, send it to the base station. The question is, who is going to collect the data and send it off? Because if everybody starts transmitting, it's going to be energy wastage. So we are going to be losing energy and the sensors will die very quickly. And therefore, we want to take this network, which is the network that I just showed before in the wireless sensor network context, and assign some things as cluster heads. So I want to make sure those red things, cluster heads, are selected, and the cluster members, which are these blue nodes, are selected. So the algorithm is supposed to, depending on the layout, figure out the cluster heads and the cluster nodes, and then the cluster heads are responsible for sending the information to the base station. So basically, the sensors sense the information, send it to the cluster head then sends it off to the sink. So what is clustering? It's a collection of algorithms that includes cluster head selection, cluster formation, how to aggregate the data from sensors. Do you take the average? Do you need all the data? Or can you do something with the data so you don't have to send this whole set of data? Because every time you transmit, you're going to lose battery energy, and you have limited battery in sensors. How is the algorithm for inter-cluster routing? How is the algorithm for intra-cluster routing of the data? So all these together form clustering algorithms. Objectives of clustering are actually against each other. So when you try to do energy efficiency, you might lose the load balancing. If you try to do load balancing, you might have more delay. So you have opposing objectives that you're trying to attack this problem with. And these are the fault tolerance, mobility, delay, energy efficiency are our main goals in clustering algorithms. So what are the approaches that has been tried? Of course, there are many approaches that have been tried. The one that I'm trying is hierarchical clustering, which is tree-based clustering. Sometimes they use density, saying if there are more nodes, then maybe you need more cluster heads there. And sometimes there's partition-based clustering, grid-based clustering, where the network is split into grids and each grid would have a cluster. So many approaches have been tried. Here is a good picture with all the clustering related. So if you start with clustering in wireless sensor networks, you can see that the process of clustering on the right is the formation and the cluster head selection. That's really what we would like to do on the right side of that original picture. And then we have what are the objectives of the clustering? As I listed, some of them oppose each other, but those are clustering objectives. And then clustering methods are on the left of the center, which talks about various density-based clustering, etc. And of course, you can have a distributed algorithm or centralized algorithm. You have a hybrid algorithm for clustering. The characteristic of a cluster becomes important. Number of clusters that you make, what is the size of each cluster. The whole idea is to keep the batteries alive as much as possible, as long as possible, so that the network won't fail. So you're collecting information and sending off to the sink. As much time as you can delay the failure of the network, because some sensors will die when the battery is no longer available. So my goal is to focus on the energy efficiency of clustering. And I want to understand how the energy is used for clustering. And then we can see how to preserve that energy. So we believe that the model indicates that energy is used when you either receive the data, send the data, or aggregate the data. Everything requires energy for the node. So the amount of energy depends on how far you send the data and how much data you're sending, right? And so here is the model for the energy expense. If you look at the top, it says ETX represents a transmission energy. So if you have to send to the distance D, L bits, there is a model for saying exactly how much energy is used for sending data. Receiving data is ERX. If you want to receive L bits, what is the amount of energy that you use. And there are some constants here called E electric, etc., which is some, constant, but L and D are the main factors. What is the amount of data you're sending, number of bits, what distance you're sending it to. So obviously you want to collect information from closer nodes, not from farther away nodes. So you want to make sure that you design it in such a way that every node uses very similar amount of energy expense and very limited energy, and no redundant work is done. So the algorithm that I use is based on breadth first search and depth first search. So basically, initially, I create a breadth first search starting at the base station. It's a breadth first search of the entire network. I'm not showing all the connections here. I'm only showing the tree. And using the breadth first search, then I do a depth first search on the same one to make sure that I have a cluster of similar size. It's not exactly the same size, but you will see that it's similar size. These are 4, these are 5. I have a limit called minimum size I need, a maximum I allow. So I run a simple algorithm to distribute my clusters so that they are at equidistance. Now this cluster head would collect information from these nodes, and this cluster head would collect information from these nodes. And the green links indicate the intercluster traversal. So it sends it to the nearest node in the next cluster towards the base station, and finally the data reaches at the base station. So clearly anything on the path is going to spend more energy. You start from the green and you have to go to the red. Anything along the path will have to carry the data from the lower cluster to the higher cluster. It's called hierarchical clustering. So obviously the cluster head near the base station is going to be spending most amount of energy because it's collecting data and transmitting data to the base station. So here is the actual algorithm that in the phase cluster formation, which we just talked about. Here is the results of the performance. Here is the network same thing that I use for wireless sensor network, except now I have for the localization, I'm using this very similar structure for this kind of clustering. Now the question is, what are my red nodes? What are my green nodes? And when I run the algorithm, what's going to happen? And here is, I hope you can see that. You see that the ones that are the one in red, there's only one node in red. It's called the base station. All the blue are regular nodes, and the green nodes are the cluster heads. So it has been split into various clusters. The number of green things you're seeing are the number of cluster heads, and the blue is the one that is cluster nodes right there. Now, how is the performance? Remember, my goal was to get a very similar cluster size. I want the cluster size to be the same, number of nodes in each cluster to be similar. And for various sensor radius, I ran this algorithm, number of sensors, I kept it as 100, and each one was iterated 50 times for each data set. I find that my cluster size is between 10 to 20 because I set the minimum cluster size is 10, and so it looks like the cluster sizes are all same, which means that energy spent by every cluster head is somewhat similar because they're collecting data from the sensors near them. So each node collects about 20 pieces of data from the nearby nodes, and therefore the energy expense should be similar. Now, how is the energy expenditure finally when I ran this algorithm? And I set here minimum cluster size to 5, and the radius of the network that we're talking about is 16. Notice that the energy dissipation at each cluster head, I had 13 cluster heads in this one, is very similar, but notice that some of the cluster heads are spending a lot of energy. The reason being maybe they are closer to the base station. The ones in the base station, near the base station, will have to carry the information from the lower branches of the tree. And by the time they end there, some of them are spending a lot of energy. And it's not a percentage or anything on the left side. It is just number of joules. It's the joules of amount of energy. So it's not that it's using 100% of the energy. It goes up to 120. So it's not really a percentage. It's the amount of energy spent on this one. And that's really where we are with respect to the two problems. And for the future work, I want to include mobile nodes. What if the nodes move during localization? How am I going to cope with that? And what if some missing distances, can I add them using some mobile nodes to make the graph localizable? The whole idea is to try to find those nodes, find the location of those nodes so we can rescue them as needed. In clustering, right now I had a fixed cluster head. What if I rotate the cluster head? And can I use some sort of rigidity structure to rotate the cluster head within the same cluster? So it's not the one cluster head all the time. For different rounds, I want to rotate different cluster heads within the same cluster. Will that help save some of the nodes before it dies like too quickly. Obviously, the cluster heads will die first because they're doing more work. They're collecting the data and transmitting. So that's the end of the talk. And now I'm open to questions if I can see the people on the